Hello and welcome to another video on GD&T. In this video, I'll be taking you through on how to set up a GD&T scheme by understanding the application of a component, what are its important functional features, and then planning out the GD&T scheme step by step. So the first important step is to understand the problem, understand what are we dealing with, what is the component which we are dealing with to start creating the GD&T scheme. So in this case, we have to create a GD&T scheme for the bracket, which is mounting a motor, and the bracket is mounted onto a base, which is shown over here, the blue color part, which is the base, and it is mounted on the base using 4 M4 bolts, and these are the clearance holes. There are 4 clearance holes. And then there is a motor which is mounted onto the bracket using 4 M3 screws. So there are 2 patterns of holes. One is for the connection between the bracket and the base, and one is the connection between the bracket and the motor. And then there is a central hole, a clearance hole for the motor for the shaft to pass through. This is the shaft of the motor. So the main purpose of the bracket is to position and mount the motor as required. So the first important step when setting up a GD&T scheme is to understand the important functional features, functional surfaces, functional features. What are the important functional features on the component? So if you look at the component, there is a fairly simple component. So there is a mounting surface which is shown at the hash surface, which is basically the resting surface of the bracket onto the base. And then there are mounting holes. There are 4 mounting holes in a pattern. And then there is the mounting surface for the motor, which is this surface. And then there is a central hole, clearance hole for the motor, and then there are 4 mounting holes for the motor. So these are the important features which are critical for the function of the bracket, which is to mount and locate the motor as required. So once we identify these important functional features, we can start defining the scheme. We can start planning the scheme. For that, we need to answer specific questions. Which features do we select as datums? And what would be the sequence of the datums, which will be primary, which will be secondary, which will be tertiary, how to construct the datum reference frame, and what type of geometric controls to apply, and where, to which features do we apply certain geometrical controls, where do we apply form control, where do we apply perpendicularity or orientation control, and where do we apply position control or any other type of control like profile. So when we look at the various features, one of the most important features is the mounting surface, that is the base surface on which the bracket is being seated. That looks to be a primary datum feature, which we can select as the primary datum feature, and should be controlled in terms of its flatness, because the flatness of this surface is important for the orientation and location of the motor as a whole. So we need to apply a flatness control over here, and we need to keep this as the primary datum feature because this is the resting surface. Then there are 4 mounting holes in a pattern. Can we have these 4 mounting holes as the secondary datum feature, because in terms of functional importance, they are the second most important in terms of function, because the bracket comes into contact on this surface first, and then it is mounted onto the base using these 4 mounting holes. So then we can keep this as a secondary datum feature. And the orientation of the pattern of holes with respect to the primary datum feature, which is this surface, becomes important. And also the interpositional deviation, that is the distance between the holes, also becomes important for mounting holes, because if they are too far apart, then they will not match with the corresponding holes on the base. When it comes to the motor interface, the mounting surface of the motor is important. So this surface on which the motor is being mounted on, that can be kept as the tertiary datum feature, that is datum feature C. The orientation of that surface with respect to the base surface of the bracket becomes important. Whether a flatness control is required or not depends on what is the flatness which can be controlled by default in the manufacturing process, and does it affect the performance of the system. Next, we look at the center hole, the motor center hole. The position of the center hole is also important. It should not deviate much because it is a clearance hole for the shaft of the motor, And also the motor mounting holes are of course very important because that decides the location of the motor and the orientation of the motor. So position control of the mounting holes is also important for motor location. So these are the various important functional features and overview of the functional features which are important and why they are important, and what can be selected as the primary datum feature, secondary datum feature. So basically we start building an idea on how to create the GD&T scheme. And then finally, when we have created a plan, we can start creating a GD&T scheme. So one possible GD&T scheme is this one. Of course, this is one possible GD&T scheme. It can be, we can have multiple variants of GD&T schemes for the same part, and they can mean different things depending on the manufacturing process and also depending on the quality inspection procedures which are available. So this is one possible GD&T scheme. So let's have a look. The first feature control frame is this one. This is the flatness control. Flatness is a form control which is not with respect to any datum. It is how flat a surface is with respect to itself. Generally for sheet metal parts, flatness control, flatness tolerance is generally on the higher side because sheet metal processing does not have that much of precision as compared to machining. Hence, we need to keep that in mind when deciding the flatness for this part. If it is a high precision part, of course, then additional operations will be required to make this surface flat, to ensure that the surface is flat, the resting surface of the bracket is flat. So flatness control is a very important geometrical control over here, and this is the primary datum feature A, which is the bottom surface, the surface on which the bracket is resting. Next, there are 4 holes, a pattern of 4 holes which are having the size of 4.4 dia with a size tolerance of plus or minus 0.1, and they are controlled with respect to their position with respect to datum A, which means that we are basically controlling the orientation or perpendicularity of the holes within a cylindrical tolerance zone. The tolerance values are not defined. These values can change depending on the application, depending on the precision required, depending on the manufacturing processes which are used. They will change. So this is just setting the scheme. We can define the tolerances later. So first line says that the perpendicularity of the holes should be within a tolerance zone of whatever the value is over here with respect to A. Second line, however, is controlling the inter-hole distance. That is, inter-hole center to center distance is being controlled within a tolerance zone of the value over here, cylindrical tolerance zone of value over here. So that is feature control frame number 2. Feature control frame number 3 is referencing the mounting surface of the motor, which is a tertiary datum feature. So this pattern of 4 holes is a secondary datum feature B. Primary datum feature A is the base surface, and these 4 holes which form a pattern is secondary datum feature B, and the tertiary datum feature C is this mounting surface of the motor, which is again being controlled with respect to its perpendicularity within a tolerance zone of this value with respect to datum A. So perpendicularity is being controlled. That controls the orientation of the motor with respect to the base surface, and this is tertiary datum C. This is the third feature control frame. And then we have position control of the center hole and the 4 mounting holes of the motor. There are 2 feature control frames, 4 and 5. Both are position control frames. The fourth annotation, that is the composite position control, also controls the center to center distance of the holes in the second line. So first line controls the pattern as a whole in terms of its positional, in terms of the position with respect to datum reference frame A, B, C. So datum reference frame A, B, C is formed by datum feature A, B and C. So first line controls the pattern, location of the pattern. Second line controls the inter-hole distance, center to center distance. The basic dimensions for that is given over here. So basic dimension for the center hole is this 30 coming from datum feature A, which is controlling the position of this hole with respect to datum feature A. And then there is hole to hole distances which are given in basic dimensions 20, 20 and also this 20, which locates this pattern from this bottom surface. So position control is applied here, position control is applied here with composite control. So this is one possible GD&T scheme. Of course, this you can making a GD&T drawing or engineering drawing is never a one-off activity. Once you create the first draft, you need to redefine tolerances as you go forward, as you learn more about the system, about the product, about manufacturing, and what is the precision required for the functional performance of the system. So step 4 is defining and redefining tolerances. If we take the example of the first one, that is feature control frame for flatness, the question is, what should I keep the flatness tolerance of a sheet metal mounting bracket with a thickness of 2.5 mm? What is the standard flatness value for a cold rolled sheet? Now, if you are considering a base value for a tolerance, what should it be? So if we refer the literature, or if we refer the standard tolerance values for flatness for a cold rolled sheet, generally the standards give a value of 0.2 mm for sheet metal parts. For high precision, generally it's in range of 0.1 mm. So depending on what we are going to use, we can put the value over here. Similarly, for the second feature control frame, where we are controlling perpendicularity and position, in first line controls perpendicularity, second line controls position. So what should I keep the tolerance value in the first line and second line? Considering that the manufacturing process is CNC drilling, if CNC drilling is being used, then in that case, what should be the value over here and here? Perpendicularity, we can keep the value of 0.15. Interhole position also, we can keep the value of 0.15 if you want good precision. Depending on the tolerance stack up analysis, which we can do for the motor mounting, based on that, these values might have to be refined. Some important questions to ask is, will the hole size be sufficient? Will the precision of the assembly affect motor performance and alignment? So this is not something which is finalized at one go. It requires more analysis as we go into it deeper. Of course, sometimes defining tolerances can be over engineering for very simple use cases. We make a drawing, we test the system out, how it is coming out, how the parts are coming out, how is the precision. If that precision is sufficient for the functional performance, then the drawing remains unchanged. But if certain aspects of, let's say for example, this value of 0.15 of perpendicularity or interhole position is not sufficient, it is causing issues in assembly or in terms of location, in terms of functional performance of the system, then that has to be refined locally. So that is generally the process of refining, defining and redefining tolerances in a GD&T scheme. So I hope this gives you an overview of how GD&T schemes are prepared and how it is an ongoing process to refine these GD&T schemes.